Okay, so today we did some enrichment problems. And if you're an online student, you can just download this file from the course website, Synthesis Enrichment, and try it for yourself, and then watch this video when you're ready. Or you can just pause this recording, try these problems, and then hit resume when you're ready. So here are problems 1 through 7, and then 8 through 12. So now we're going to go over them. Oops. And talk about each one. So the instructions say that if more than one reaction works, give me both. So the molecule that we want, 2-methyl-2-heptanol. All right, there are two reactions so far that we've learned that will produce an alcohol, right? Reaction number 1 is we could reduce a ketone, right? If we hydrogenate a ketone, that'll give us an alcohol, right? So we want 2-methyl-2-heptanol. So that's 7 carbons. 1, 2, 3, 4, 5, 6, 7. 2-methyl. Oh boy, I just realized that's not going to work for 2-methyl-2-heptanol, will it? It'd work for 2-methyl-3-heptanol, but you can't have a ketone here. 1, 2, 3, 4, 5. That wouldn't work. For some reason, I was thinking it was 2-methyl-3-heptanol. So no, ketone hydrogenation won't work, right? Because you can't have 5 bonds. So there's only one reaction that'll work. If it were 2-methyl-3-heptanol, you could reduce a ketone. But because it's 2-methyl-2-heptanol, there's only one reaction that'll work. Yeah, alkene hydration. So you want 2-methyl-2-heptanol, 1, 2, 3, 4, 5, 6, 7. So where does the double bond need to be?
On the left.
On the left? Would it work the same if you had it on the right? It'd work either way, right? Because if you react this with H2O, oops, right, the hydrogen's going to go here, and the OH is going to go here. If the double bond was here, you'd get the hydrogen going here, and the OH would still go there. So either one would work. You could have the double bond on the left, or you could have the double bond on the right. What catalyst do we need? This requires acid catalyst, right? And following Markovnikov's rule, 1, 2, 3, 4, 5, 6, 7, you get your 2-methyl-2-heptanol. Again, if it were 2-methyl-3-heptanol, you could reduce your ketone. I just wasn't thinking. But that's the only one that we've talked about so far that would do this. We good on this one? Okay. Reaction to produce hexane. Boy, there are a lot of things that could produce hexane. Right? There are two options that I came up with. What's one that you came up with? Right, alkene hydrogenation. Why are my markers getting low? Change that out. Now, to get hexane, 1, 2, 3, 4, 5, 6, does it matter where the double bond is? As long as it's in there somewhere, right? You could have made it here, 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 anywhere, right? The alkene, anywhere. Why does it not matter where the alkene is? Right, you're putting a hydrogen on each one. What's the catalyst here? Nope. You could use platinum or palladium, and you need temperature. And then you're going to get 1, 2, 3, 4, 5, 6. So that's option number 1. There's another option that would work too. What's the other option? Yeah, alkyne. And again, does it matter where the triple bond is? Nope. As long as it's in there somewhere. And the only difference is instead of having H2, what do you need to have? 2H2, right? Catalysts are still the same. Feeling good about that one? That was that was the first reaction we actually learned. The hydrogenation. Alrighty. Let's see what else we've got here. Let's put this on its own page. Two methylcyclohexane. I came up with 2 options. Did you? Mm-hmm. Diels-Alder works for one of them. Oh, I can't get it on where I want it on the screen. There we go. Excuse me. Diels-Alder works. Right, because we want 2-methylcyclohexane. So if your diene looks like that, your alkene looks like that. If you remember A, B, C, D, E, F, bond forms here and here. The double bond gets put right there. That gives you 2-methylcyclohexane.
Instead of putting your methyl on the other one, or on the, what'd you just call it?
On the diene?
Yeah, can I make the other one ethyl with the double bond?
Put it right here.
Yeah, does that work or no?
So if you had, let's see, this, that would have given you that, which would be 3-methyl. 1, 2, 3, actually 4-methyl. So if you put it right here, is that what you're asking?
Yeah.
Yeah, that wouldn't have worked. Or if you put it right here, it'd still be too far away. You need it to be on the double bond. That's why you put it right there. Does that make sense?
Yeah.
And then there's another option. What's another way that you can make an alkene? It's the cursor. If you dehydrate an alcohol, will that give you an alkene? Yep. Alkene. Dehydration. Right? So if we want 2-methylcyclohexene, we need to follow Satsev's rule, right? If you have this, what does Satsev's rule say? It says the more substituted alkene is the favored product, right? So the double bond going right here is the major product. And is that the desired product? Yeah. That's still 1, 2, 2-methyl. And then your other product's water. Do we agree on that one? Any other ones you thought of for number 3?
I didn't know how to do that.
Okay, we can do that one. So number 4 asks you, and there's only one option that you would know. How would you make cyclopentanone? There's only one reaction that we've learned so far that would allow you to produce a ketone. It's alcohol what? Oxidation. If you take an alcohol and it's secondary alcohol and you oxidize it, you get a ketone. If it's a primary alcohol and you oxidize it, you get an aldehyde. So if you oxidize an alcohol, that'll give you a ketone. So we want 3-chlorocyclopentanone. 1, 2, 3, 4, 5. So if we start with 1, 2, 3, 3-chlorocyclopentanol, and we oxidize this, you can use whatever oxidizer of your choosing, you will get your ketone, 3-chlorocyclopentanone. And that's the only one that we've talked about that would produce a ketone. Does that one make sense?
Yes, I used to have it on my chart.
Oh, okay. Oxidizing an alcohol. If it's primary alcohol, you get an aldehyde. If it's secondary alcohol, you get a ketone. All right, number 5. Bromo cyclohexane. I came up with 2. What reaction did you, how many reactions did you come up with?
One of them is alkene hydrohalogenation.
Yep. Number 1, alkene hydrohalogenation.
Can you have an alkyne? 1, 2.
That would give you too many bromos if there were an alkyne. So if you have bromo cyclohexane that you're wanting, does it matter where the double bond is in that ring? No, it's not going to matter, right? Because you're going to be reacting this with HBr. Markovnikov's rule is not going to apply here, right? Because one hydrogen goes here, one bromine goes here. That gives you bromo cyclohexane. There's another option that would work too. What if you take an alkene, a bromo alkene, just a regular old alkene hydrogenation. Put H plus as our catalyst there. So what, for instance, what if you had this? Try not to stand in front of them. What if you just had that? Plus H2. You'd reduce the double bond, that'd leave you with bromo cyclohexane. Those are the same thing, right? So either one of those would have worked. Any questions on 5? Doing good on that one? All right, number 6. Now, we haven't named carboxylic acids yet. That's why I said it's a 5-carbon chain with a COOH functional group. We're going to name carboxylic acids the Monday after spring break. So the day we come back, we'll name carboxylic acids. It's not difficult to name. But you do know how to make a carboxylic acid. How can you make a carboxylic acid? There's only one way to talk about it. Right. Aldehyde oxidation. Good. And aldehydes oxidize super easily, right? So if you just start with pentanal, 1, 2, 3, 4, 5, and then use any oxidizer of your choice, you'll get pentanoic acid. Which is what we're looking for. That was the only one we've talked about on how to make a carboxylic acid. We haven't talked about anything else. Yes, it's this hydrogen that becomes an OH. Yes, that double bond is intact because this right here is the carboxylic acid functional group, COOH. COOH. That's the functional group right there. Okay. For number 7, I came up with 2 reactions. Did you? 2 bromo, 2 hexene. Okay. So it's technically 1 reaction, but there are 2 possible starting places. One's just better than the other. How can we make an alkene? Well, if it's in a ring, we can do Diels-Alder, but this isn't a ring, this is linear. So how can we make an alkene otherwise? If we do alcohol dehydration, right? That gives us an alkene. And there are 2 options. One is better than the other, but the other is acceptable. All right, so if you start with X, 1, 2, 3, 4, 5, 6, BROH, and you dehydrate that, what's the major product going to be? Where's the double bond going to go as the major product? It's going to go right here, right? Because that's the more substituted. 1, 2, 3, 4, 5, 6. 2 bromo, 2 hexene, right? Now, you also could have done 1, 2, 3, 4, 5, 6. This, right? But this one isn't as good. Why is this one not as good?
Because either one of them are, where would you put the double bond?
It could go here or here, right? You're going to get both products. It gives 2 products. You're going to get 1, 2, 3, 4, 5, 6. You're going to get your product of interest, but you're also going to get the version of it where it's 1 instead of 2 hexene. Right? So this one is best, but this one is acceptable. Do you see why this one's better than this one is? Right? Because here, this is the major product, whereas here you're going to get a mixture of the double bond on carbon 2 and the double bond on carbon 1. Make sense?
And does it have a catalyst?
For dehydration? Yes. It's H+, isn't it? Oh, and I forgot our other product. What's our other product? Water. We're good on number 7? All right, number 8. There's only 1 reaction that we've talked about so far. Yes, that's the only one we talked about. Because you're trying to make an aldehyde, right? So the reaction is oxidation. And since we're trying to make an aldehyde, we need this to be a primary alcohol, right? So HEP is 7. 1, 2, 3, 4, 5, 7. We want 3 ethyl, 2 methyl, heptanal. Right, so that means that this carbon is number 1. That's the one that needs to get oxidized. So 1, 2, 3, 4, 5, 6, 7. This, that. That gives us our product of interest. Do we agree on number 8? All right, in number 9, (2,3-dichloroheptane). There's only one reaction that we've talked about. What would that be? Right. Alkene halogenation. So hep again, 1, 2, 3, 4, 5, 6, 7. We want this to be 2,3-dichloro. So where does the double bond need to be? Between 2 and 3, right? And then we're reacting this with Cl2. Do we need any catalysts here? No, this does not require a catalyst. 1, 2, 3, 4, 5, 6, 7. Cl, Cl. So that's a review problem too. That's the second reaction we learned this semester. And excuse me, I don't know why I'm coughing so much this morning. Chlorobenzene. We talked about this one pretty recently. How do you make chlorobenzene? There's only one reaction we talked about.
Benzene halogenation.
Right. Benzene halogenation. So you take your benzene, and what do you react it with? You do Cl2, right? And then what would your catalyst be? Fe or FeCl3. Either one would work. And then what are you going to get? You get 2 products. You get chlorobenzene, and what's your other product?
HCl.
Plus HCl. Good. Halogenation. Talked about that one, what, 3 weeks ago? All right, number 11, we're trying to make an alcohol. (2-ethyl cyclohexanol). I came up with 2 options. Oops, off the screen there. What's one option? Alkene hydration will do the job. Yep.
And then, you called it something else, but I'm sure I have carbonyl reduction.
Carbonyl reduction, yep, well, specifically, is it going to be an aldehyde or a ketone that we're reducing? It'll be a ketone, right? So when we're hydrating this alkene, 2-ethyl cyclohexanol, where does the double bond need to be? There is a specific place where we want it to be. If we have the double bond here, and then our ethyl group here, one of these is, there's going to be a very distinct winner, right?
Is it your ethyl group on here?
You want 2-ethyl? So if you want the alcohol to go right here, so that this becomes carbon number 2. You see what I'm saying?
Yep.
Because the alcohol is going to go here because you want the ethyl group to be on number 2. If you react this with H2O, right, one of them's going to get hydrogen, the other one's going to get alcohol. Did you have it somewhere else?
Yeah, but I did it wrong. That makes more sense.
Where did you have it? Just out of
I had
curiosity.
my ethyl like on the end of the double bond. So I thought that would be 1, 2.
So if you had this.
Yep.
Okay, let's talk about what would happen if you did that. Hydrogen's going to go here. OH is going to go here, right? Because hydrogen's going to go to the least substituted. That won't give you the product you want. That would give you that, right? And that's not what you want. That's 1-ethyl. you want 2-ethyl. So that's why you need to space it a little bit further away.
I wasn't thinking.
Now you'll also get the other version, right? You'll get 2 products because you'll also get a version where the OH is over here. You're going to get 2 products. You'll also get that's something you're just going to have to deal with, right? You'll get 2-ethyl and 1, 2, 3, 4-ethyl. Well, actually 1, 2, 3-ethyl, I should say, right? Because if the double bond's here, you're going to get 50-50 mixture. So you will have 2 products to contend with. But you can't have it right here because then your only product is going to, your major product is going to be this. So that's the version for alkene hydration. And then what would your other reaction be?
Ketone reduction.
Yes. If you called it a carbonyl reduction, I'm not going to freak out over that. Call it a ketone reduction. I mean, you can call it ketone hydrogenation too, would work too, right? Because you're reacting it with H2. So where does the ketone need to be? Relative to the ethyl group, where does the ketone need to be? 1 away, right? So long as they are next door to each other. What am I reacting this with? H2. And that's why I say you can call it hydrogenation. Do we agree on number 11? And then last one. One dimethyl, 1,1-dimethoxypentane. That's number 12. What do we do there?
I didn't know. It has something to do with ketone.
That's going to be the addition reaction. Right? The reaction is addition. Okay, so let's think about this. Let's just draw this first. Pentane, 1, 2, 3, 4, 5. I wouldn't ask you one this hard on a test, by the way. This is just kind of a stretch your mind question. 1, 2, 3, 4, 5. And then we want 1,1-dimethoxy. O. So think back to Wednesday? Yeah. What reaction gives us 2 ethers? Do you remember? Well, all of these are synthesis reactions, right? Because we're making some product that we're interested in.
Yeah.
Okay, so let's think back to our addition reaction that we learned this week. If you have pentanal, 1, 2, 3, 4, 5, and methanol, let's go through that again. Let's get rid of this. All right, it's going to be a 2-step reaction. So the hydrogen is the positive part, the oxygen is the negative part, oxygen's the negative part, carbon's the positive part, right? So the hydrogen goes on the oxygen, the OCH3 goes here. So that gives 1, 2, 3, 4, 5. OH, yes. And then what's the other thing here? It would be OCH3, right? And that's an intermediate. And then what happens in step 2?
Intermediate comes down.
Right, we redraw our intermediate, 1, 2, 3, 4, 5. OCH3, OH, and then what's this reacting with?
So what's the second thing?
Another alcohol, right? Right, we displace OH as H2O with OCH3. So we get 1, 2, 3, 4, 5 OCH3, OCH3, right? That's 1,1-dimethoxypentane. That's the product we're interested in. So I wouldn't ask one this difficult on a test because I didn't make you learn how to name molecules with 2 ethers in it. But I thought maybe you could figure it out. So just a little bit of a challenge problem there for you. But do you see how to do this? We had to figure out what 2 molecules to begin with. How did we do that? Well, the pentane means that that was pentanal, right? Because whatever this chain is, that's the chain on the aldehyde, right? And then whatever if this is methoxy, ethoxy, propoxy, butoxy, whatever, that's the chain on the alcohol. Does that make sense? These are the 2 pieces that came from the alcohol. This is the piece that came from the aldehyde. So it's just coming from looking at the name. Does that make sense? Any other ones you want to talk about? Any other questions on this? So this was kind of a summary of all the stuff we've been talking about so far in terms of reactions, right? Feeling good?
Yeah.
All right, well then that's where we're going to stop.